moving on with chapter 2, which is going to be the properties of the fluid. So here, it's just stating that a drop forms when a liquid is forced out of a small tube. The shape of the drop is determined by a balance of pressure, gravity, and surface tension forces. Right, because if this drop was a drop of gas, it would not be together. It would not have the collective forces holding it together, right? And so if you have a lot of pressure, or a lot of gravity, or even different materials have different surface tensions, then maybe the shape would look different than a drop. Here's the objectives. We're not going to go through all of them, but let's talk about what a property is. So this is very similar to thermo in that it's any characteristic of a system, right? So the system that you are looking at, any characteristic of that system is a property. And familiar ones that we have is P for pressure, T, capital T for temperature, and volume, capital V, and then mass is M. Properties are considered to be intensive or extensive, right? Intensive properties, those that are independent of the mass. Okay, same as thermo, if you've taken that, or if you are, they are independent of the mass, such as temperature, pressure, and density. It doesn't matter. It doesn't matter how much of the material that you have. The temperature is going to be the same. You could have a bucket of water or a drop of water, and they can still be the same temperature. Okay, you can have a bucket of water or a drop of water, and the water is still going to have the same density. It is intensive. I like to think intensive, independent, right? It doesn't matter how much. Extensive properties, those are the values that do depend on the size or extent of the system, right? So it matters how much you have. And then specific properties are extensive properties that are per unit mass. So anytime we have specific on there, you'll see that it's taken on a per unit mass basis. And here's just a note of what those are. So matter is made up of atoms that are widely spaced in the gas phase. It is very convenient to disregard the atomic nature of a substance and view it as continuous homogeneous matter with no holes. That is a continuum. So let's talk about what a continuum is here. Oops. Okay. The continuum idealization allows us to treat properties as point functions and to assume the properties vary continually in a space with no jump discontinuities. So when we start taking the properties of this matter, right, then we can view it as a continuum, and we can treat those properties as point functions and assume that no matter where you are, no matter where you take it on that function, no matter what point you use, that the values are going to be the same. The properties are going to be the same, and that they're not going to vary with time and space, right? They're going to be consistent, continuum. That's going to allow us to calculate something, right? So when we start using tables and start pulling data, molecular data, stuff like that, what is the density of something, right? What is the enthalpy of something? What is the internal energy of something? All of those things. What we conclude when we're talking about a continuum is that no matter where you look at on that matter, right? That's that subject that we're looking at, that the properties are going to be continuous. This idealization is valid as long as the size of the system we deal with is large relative to the space between the molecules. This is a case of practically all problems. So not something super important, because it's the case in practically all problems, right? And in this text, we will limit our consideration to substances that can be modeled as a continuum. What that's saying is basically we're not going to worry about the cases that's not, okay? Okay, the length scale associated with most flows, such as seagulls in flight, is orders of magnitude larger than the mean free path of air molecules. Therefore, here, and for all fluid flows considered in this book, the continuum ionization is appropriate. So again, we're just using it. It's because we are studying things that we can see, flows that we can see, things like that. So let's talk about this density and specific gravity. So density is rho equals mass over volume, right? And that is in the units kilograms over meters cubed. And then we have specific, which is just the inverse of density. So you have specific volume, which is just the inverse of density. Okay? Specific volume is the ratio of the density of a substance to the density of some standard substance at a specified temperature, usually water at 4 degrees Celsius. We use water a lot because it's so relatively available. And so when you're looking at using a working fluid, you want to use something that we have a lot of, that's cheap, that's relatively accessible. So, and that's worldwide, right? So if you were comparing everything to helium, right? Helium's common, but much harder to get than water, right? Or if you start looking at materials that are not in all regions or are not readily accessible in all regions, right? So water is an easy one for us to compare things to. Specific weight is the weight of a unit volume of a substance. So it's just the weight of a unit on a specific, like on a mass basis. Okay, density is mass per unit volume. Specific volume is volume per unit mass. So it's just the inverse. That's all we're talking about. Okay, and then here's a table that gives some specific gravities of substances at 20 degrees Celsius and 1 atmospheric pressure, unless stated otherwise. And so you see our basis there is water at 1. So the density of ideal gases, when we talk about the equation of state, that's any equation that relates to the pressure, temperature, and density or specific volume of a substance. So if you have an equation that relates to pressure, temperature, and density or specific volume of a substance, that's going to be the equation of state. And also with that, those pressure, temperature, and density or volume, more specifically, those have a relationship that all work. When you start messing with pressure, chances are the temperature is going to change or the volume is going to change and vice versa. And so that's a triangular relationship between those. So any equation that relates to those is equation of state. Ideal gas equation of state is the simplest and best known equation of state for substances in a gas phase, and that is PV equals RT or P equals rho RT, PV equals MRT, all kinds of things. Here, just remember we do have a universal gas constant, and that's going to be R, and that's 8.314 kilojoules over kilomole times Kelvin. So that's that universal gas constant that we're going to use. And it's just different forms of these. Again, we're not going to spend too much time in this theoretical portion trying to go through all of the equations. That's meant for more of the time that we will actually be working them. So we have temperature scales. Of course, we have the Kelvin scale. It's a thermodynamic temperature scale in the SI system, and then the Rankine, which is in the EE, right? So this is a simple conversion to get it for Kelvin and Rankine. And again, just remember that we're looking for those homogeneous units, right? We need those homogeneous units. So if you have two different temperatures, if you have a Kelvin and a Rankine scale, you need to get those to one scale. You need to be using either the SI or the EE. And sometimes it will specify, right? If it's giving you two different data, it'll say, give your answer in the SI system or give your answer in the Kelvin scale. Give it in Rankine, things like that. Okay? So an ideal gas is a hypothetical substance that obeys the relation PV equals RT. And I want you to know that we use a lot of ideal gases that are not 100% ideal, but we equate them to ideal, right? So the ideal gas relation closely approximates the PVT behavior of real gases at low densities. At low pressures and high temperatures, the density of a gas decreases and the gas behaves like an ideal gas. For those examples that we kind of equate to this ideal gas, this PV equals RT behavior, this PVT behavior, in the range of practical interest, many familiar gases such as air, nitrogen, oxygen, hydrogen, helium, argon, neon, and carbon dioxide can be treated as ideal gas with negligible error. That's why it is a true hypothetical substance. So for us to get a 100% accurate answer, we would have no negligible error. But for us to be able to use this on a gas, we will not be able to get a 100% answer, right? We will have substances that we can use with this PVT behavior of the ideal gas in our equation of state within, and we can use them on these items, air, nitrogen, all of these, and just get a negligible error. So it's basically the best that we've got, right? And that should be a clue into, because anytime we see ideal right here, ideal is hypothetical. Ideal is the very best we can get, the most accurate, the most efficient. Ideal is like the peak of the mountain. There's nothing better than that. And so what we know is that everything real world, when we talk about real world air, real world nitrogen, real world oxygen, things like that, it's going to fall a little bit short. And that's where that negligible error comes in. Dense gases such as water vapor in a steam power plants and refrigerant vapor in refrigerators, however, should not be treated as ideal gases since they usually exist at a state near saturation. And that's because we're getting in to that vapor portion. We're going to have more saturation in there. And so therefore, those are not going to be an ideal gas. Okay? So we have Tsat, which is saturation temperature. This is a temperature at which a pure substance changes phase at a given pressure. Okay? So reference to the pressure. That's our saturation temperature. And then just the opposite, our Psat is saturation pressure. Same thing, but at a given temperature. Vapor pressure, PV, is the pressure exerted by its vapor in a phase equilibrium to its liquid at a given temperature. It's identical to the saturation pressure, Psat, of a liquid. So PV equals Psat. And then finally, with partial pressure, that's the pressure of the gas or vapor in a mixture with other gases. So for example, atmospheric air is a mixture of dry air and water vapor, right? So because we know that our atmospheric air is not completely a gas, right? So we have a dry air and a water vapor. We have moisture in that, and you know that by humidity. The atmospheric pressure is the sum of the partial pressures of dry air and the partial pressures of water vapor. So you're taking the pressures of that dry air and of that water vapor, and the sum of those become the total atmospheric pressure, which thus makes the dry air and water vapor partial pressures because it's part of a whole mixture. Okay, and so here's just some saturation or vapor pressures of water at various temperatures. So you can see that over here. And then here it just has water molecules in a liquid phase. And then we have water molecules in a vapor phase. So you can see that in a liquid phase down here, right here, things are much more organized, right? It looks like water, like you have a surface tension, right? You have a free surface there. And, this could be like a little spill. But then when you're talking about a vapor phase, they're all spread out. This is a gas. It's just filling up the area that it can, that's available, whether it be held by gravity or by a room, anything like that. But it's much less organized. Vapor pressure, saturation pressure of a pure substance, example water, is the pressure exerted by its vapor molecules when the system is in phase equilibrium with its liquid molecules at a given temperature. So it's just telling you how these different ones relate, but I feel like it's easier to see on the graph. So moving on to cavitation bubbles, which are seen here on the right in a photo. So what happens to extrapolate these is the liquid pressure in a liquid flow system drops below the vapor pressure. So the liquid pressure in a flow system drops below the vapor pressure at some locations, and the resulting is an unplanned vaporization. And so that's called the cavitation bubbles, since they form little cavities that you can see. They collapse as they are swept away from the low pressure regions, and they generate highly destructive, extremely high pressure waves. So, and you can see kind of in a wave formation here. You can see like waves in it, right? Where that destruction is. So it's a phenomena which is a common cause for drop in performance and erosion of impeller blades, and that's called as cavitation. So the phenomena and the destruction causing the drop in performance, that's called cavitation, and it's an important consideration in the design of hydraulic turbines and pumps. And so just ways to mitigate that. So here is energy in specific heats. Energy can exist in numerous forms, and it's thermal, mechanical, kinetic, potential, electric, magnetic, chemical, and nuclear. And their sums constitute total energy. So total energy of a system is just all of the types of energy added up. All the forms of energy. So the sum of all energies. That is the total energy. And then you have two different forms of energy. So that's going to be the microscopic and the macroscopic. And you probably have taken macro and microeconomics. And so micro is just a smaller degree of looking at something, and then a macro is a larger scale. So macro is a system that possesses as a whole with respect to some outside reference frame, kinetic, potential energy, something like that. So it's the whole system, and you're able to compare that whole system to an outside entity, right? But when you're looking at a microscopic form of energy, that's related to the molecular structure of a system, the degree of molecular activity. So it's looking at it kind of under a microscope, right? Internal energy, which is denoted by U, is the sum of all the microscopic energies. So for everything that you find in a microscopic form of energy, if you add all of those up, that's U. We refer to sensible and latent heat as internal energy as heat. In engineering, those forms are thermal energy. So that's just a little note there. Kinetic energy, which is denoted by Ke, is the energy that a system possesses as a result of its motion relative to some reference point. So a starting point, and then the change in that is that motion, and that's going to be kinetic energy. So think of kinetic energy as the moving energy. Okay, and then potential energy is the energy of a system that it possesses as a result of its elevation or gravitational field. So the potential energy is the potential to move. So the potential to exhibit the kinetic energy. The potential energy is like the stored energy. And typically that's because of elevation or gravitational field. And that's because, say you are holding something like a ball, and right before you throw it, right before the moment that you throw it, that ball has all of the potential energy, right? Once you throw it, that potential energy is changing to kinetic energy, right? Because it's moving now. It's moved from your hand, which is that reference point, and it's going to some other point, right? But what's stored up there right before you move it is its potential energy. So at least 6 different forms of energy are encountered in bringing power from a nuclear plant to your home. Nuclear, thermal, mechanical, kinetic, potential, and electrical, right? So you have the nuclear energy, which is transforming whatever source that this nuclear plant is getting their energy from. It could be a couple of different sources. It could be solar, it could be fossil fuels, it could be whatever. So you have nuclear energy coming in, and then that's transferring it into thermal energy, which is then transferring it into mechanical or work, which is then kinetic energy, and then magnetic, and then finally into electrical energy. So here, oh, just a note here. I explained nuclear as far as like fossil fuels and solar. I meant not particularly to nuclear, but any sort of energy plant. This is the same kind of thing. So if you have a nuclear, like a chemical reaction, right? Or if you have just anything, solar power panels, if you have wind turbines, if you have water, if you have any sort of energy that you're grasping from the outside or you're extrapolating from some natural form, it kind of follows this process if you're bringing it into usable energy: thermal, mechanical, kinetic, magnetic, and then electrical. Sorry about that. I'm sure you guys were like, nuclear and the sun. So here's a formula up here for enthalpy, and then followed by energy of a flowing fluid. Just want to make note, here's the energy of a flowing fluid, and you see flowing is denoted because remember when we use a subscript, that's kind of like a name tag for us to know what energy you're talking about. And then here you have specific heat at a constant volume, which is denoted by CV. So constant is the C, and then V right here, constant. And then what type of constant? It's going to be a volume. So remember the mass is not changing. In a moment, we're going to do the same for constant and then pressure as well. So here, specific heat for a constant volume, the energy required to raise the temperature of a unit mass of a substance by 1 degree as the volume is maintained constant, okay? So if you have a specific heat at a constant volume, what this specific heat is, it's saying, hey, we need this amount of energy to raise the temperature per unit mass, of course, because that matters, of whatever the substance is by 1 degree, but we have to maintain the volume as constant. And then the same situation, specific heat at a constant pressure, the same thing, the energy required to raise the temperature per unit mass of this random substance by 1 degree if the pressure is maintained constant. So internal energy, U, represents the microscopic energy of a non-flowing fluid per unit mass, whereas enthalpy, H, represents the microscopic energy of a fluid flowing per unit mass. So here we've got compressibility and speed of sound. So coefficient of compressibility, okay? We know from experience that a volume or density of a fluid changes with a change in its temperature or pressure. Fluid usually expand as they are heated or depressurize and contract as they are cooled or pressurized. But the amount of volume change is different for different fluids. So what that means is it means if you give the same amount of temperature or the same amount of pressure, that expanding or contraction, those volume changes are going to be different dependent on your fluids. And so therefore, you define properties that relate volume changes to the changes in pressures and temperatures. So what we're saying is we're saying, hey, if we compress this or if we expand this, our volumes change. Even if we're keeping the temperature and pressure consistent, our volume changes and it's dependent on whatever working fluid we're using. And therefore, we have specific properties that relate to the volume changes. So specific volumes for each specific entity. So two of these properties is the bulk modulus of elasticity, and that's a K, and then the coefficient of volume expansion, and that's B. And here you just have fluids like solids compress when the applied pressure is increasing from P1 to P2, which is P state 1 and pressure at state 2. Okay, and so this is just saying the pressure at state 2 is greater than the pressure at state 1. Okay, and so what we did is we went from pressure, the pressure at state 1, and we compressed, and obviously we got a lot smaller. And so therefore the pressure that we are experiencing at state 2 is much greater than the pressure at state 1. Here we have the coefficient of compressibility, the bulk modulus of compressibility, or bulk modulus of elasticity for fluids, and that's K, and that's taken into account that the temperature is constant right here. Okay, so what does this do? This represents the change in pressure corresponding to a fractional change in volume or density of a fluid while the temperature remains constant. Okay, and so here it says, what is the coefficient of compressibility of a truly incompressible substance, which V is equal to constant? For this, I want you to remember that liquids are typically explained, you see here at the bottom, is typically considered to be incompressible, right? And so here when you come back up, a large value of K indicates that a large change in pressure is needed to cause a small fractional change in volume. And thus a fluid with a large K is essentially incompressible, right? Okay, so therefore, if we need to compress a fluid and we are giving it a very large amount of pressure, and therefore it has a very large K, that coefficient of compressibility, very large. And if we're only extrapolating out small fractional changes in volumes, then it is essentially incompressible. And it's typical for liquids because liquids are typically incompressible. Remember, if you are squeezing a drop of water, the water will displace between your fingertips, but you're not going to squeeze it to a smaller. It's not like taking a piece of paper and crumbling it up, and the more pressure you apply, the smaller it does get, and it stays that way. It's not the same for liquids. They just displace. I want you to think of water hammer because it has a whole page to it, a whole slide here. When you have an abrupt restriction, you can kind of think of it like a vacuum, and I'm sure you've experienced this in your house. If you have a flow of air and maybe you've got windows open, right, and your doors are open, and if you abruptly close one of them, it can kind of suck one of the other doors and it can slam it shut, and it creates that vacuum inside. That's similar to what's happening here, but because we're working with liquids and not air inside of the pipe, you experience that acoustic wave, and it strikes the pipe surfaces, bends, and valves as they propagate and reflect along the pipe. And so it causes that vibration. However, that's still a force, right? The acoustic wave, that is moving energy, right? And so that they can be quite destructive. They can lead to leaks or maybe small cracks that were already there, and they can make them bigger. They can extrapolate just the potential fails within the system and even cause structural damage. So here are some of the arresters that we can use to kind of mitigate those water hammer happenings. So a large surge tower built to protect the pipeline against water hammer damage. So that's a huge one, and you can see the water. You can see it going here and then here to mitigate it. And then much smaller is used for supplying water to your household washing machine. Here, so we have them in our house. So for an ideal gas, P equals rho RT, and here's the conversions. Basically what that equates to is that compressibility factor here. K ideal for ideal gas is equal to P, and that's in the unit pascals. The coefficient of compressibility of an ideal gas is equal to its absolute pressure, and the coefficient of compressibility of the gas increases with increasing pressure. So it's just saying that it has a like relationship. And here's the ideal gas as well. Okay, and so here it's just telling you the percent increase of the density of an ideal gas during an isothermal, which is temperature is constant, right? So here it's isothermal. Okay, compression is equal to the percent increase in the pressure. Isothermal compressibility is the inverse of the coefficient of compressibility. So you have K, and then you have 1 over K for isothermal compressibility. The isothermal compressibility of a fluid represents the fractional change in volume or density, corresponding to a unit change in pressure. Okay, so you also have a coefficient of volume expansion. So we had the compressibility factor, now you have the coefficient of volume expansion. Okay, the density of a fluid depends more strongly on temperature than it does on pressure. Okay, so that means that it is influenced more when you have temperature changes versus pressure changes. The variation of density with temperature is responsible for numerous natural phenomena, such as winds, currents in the oceans, rise of plumes in the chimney, the operation of hot air balloons, heat transfer by natural convection, and even the rise of hot air, and thus the phrase heat rises. To quantify these effects, we need a property that represents the variation of the density of a fluid with temperature at a constant pressure. And this is natural convection over a woman's hand. The coefficient of volume expansion, which is volume expansivity, the variation of the density of a fluid with temperature at a constant pressure. Okay, so these are just giving you formulas here. A large value of beta for a fluid. So if you have a large B value for fluid, it means that there's a large change in density with temperature. And remember, we just talked about that temperature has a large effect on fluids. The product of beta times temperature, or times a change in temperature, represents the fraction of volume change of a fluid that corresponds to a temperature change of T at a constant pressure. So this is holding constant pressure, that it's the fraction of the volume change with a change in temperature, so between states. The volume expansion coefficient is an ideal gas. P equals rho RT at a temperature T is equivalent to the inverse of the temperature. And so you see that beta of an ideal gas is equal to 1 over T. So here in the study of natural convection currents, the condition of the main fluid body that surrounds the finite hot or cold regions is indicated by a subscript infinity, to serve as a reminder that this is the value at a distance where the presence of the hot or cold region is not felt. In such cases, the volume expansion coefficient can be expressed approximately as below. And that's because things like temperature, right? And so hot or cold is always heat. It's just the measure of the heat, right? So if something is hot, then it contains a lot of heat. If something is cold, then it contains a little amount of heat. And temperature is a continuous measurement, right? So even if I were to take your temperature right now, with the thermometers, let's say it says 98.6 degrees, right? That's because that's what that temperature and what household thermometers have, the capability of measuring is 98.6 degrees or 98.65, right? But of course we have measuring devices, we have thermometers that are to a much greater detail of 2 degrees, right? It can go to 10, 20, but we know mathematically and by the laws of infinity that you can keep taking an exact temperature of something to an infinite amount of decimal places. The only reason that we can't is because we don't have a thermometer that's capable of doing that, right? That doesn't exist. However, if I were to take your temperature infinite amounts of time, so not just have an infinite temperature with infinite decimal places, but if I were to take it every second or every half a second or every quarter of a second, right? I can keep breaking down the time. I know that it is always going to be changing, right? It's never going to be the exact same because temperature is kind of like a slider. It's not something that just stops. It's always fluctuating because our universe is always trying to reach equilibrium. So it's always changing. It may change microscopically, and the changes that happen may be negligible and unimpactful. But we do denote that the condition of the main fluid body that surrounds the finite hot or cold regions is indicated by the subscript infinity. And it's to serve as a reminder that this is the value at a distance where the presence of hot or cold region is not felt, right? At an infinite distance or an infinite region. Okay? And the combined effects of pressure and temperature changes on the volume change of a fluid can be determined by taking the specific volume to be a function of T or P. And that's because when we are talking about temperature and pressure, it has a direct relationship with volume. Those three things happen, right? So if you have a gas and you raise up the temperature, you can absolutely be expanding that volume and keeping the pressure the same, right? And so these have a triangular relationship where they can definitely affect each other, okay? And the fractional change in volume or density due to changes in pressure and temperature can be expressed as below, right? The change in volume over volume equals a negative change in rho over rho. And that's approximately beta times the change in temperature less alpha times the change in pressure. So here, vapor clouds around an F-18F. Super Hornet as it flies near the sound of speed. So you can see that wave there, that shock wave, right? The sudden drop in temperature produces condensation of water vapor or a visible vapor cloud. Isn't that amazing? You can just see it right here, right? As it's approaching that speed of sound, that shock wave that it experiences. And you can even see some over here. We see some here around it. You can almost see the discoloration, the drag that's being experienced and how it gets thicker and thicker and thicker as it gets to the plane. Because planes, remember, it's sticky, it's sticking. The variation of the coefficient of volume expansion of water with temperature in the range of 20 degrees Celsius to 50 degrees Celsius. So this is just showing you a relationship. Speed of sound and Mach number. Okay, so the speed of sound, which is sonic speed, is the speed at which an infinitesimally small pressure waves travel through a medium. Okay, so very, very, very small. It's the speed at which very, very, very small pressure wave travels through a medium. Okay, and so here we have it denoted as a piston, and the wave moving forward is here, and then the stationary fluid. And you have this under volume in X and P in X. And it's the propagation of a small pressure wave along a duct here, a control volume traveling with the wavefront. And so here you see it's a control volume wave. Okay, so control volume moving with the small pressure along a duct. And then we have formulas here for any fluid. And then, of course, a special one, because we always have a special one for ideal gases. Okay, so it's just defining what speed of sound is, and then showing you how you can propagate those with formulas. Okay, The speed of sound in air increases with temperature. At a typical outside temperature, C is about 340 meters per second. In round numbers, therefore, the speed of sound, the sound of thunder from a lightning strike travels about 1 kilometer in 3 seconds. If you see the lightning and you hear the thunder less than 3 seconds later, you know that the lightning is close to you and it's time to go indoors. So I think we all did this when we were a kid, right? We would count to see how far away it actually was. So here we have Mach number, MA, is the ratio of the actual speed of fluid or an object in a still fluid to the speed of sound. So it's just those ratios to give you that Mach number. Okay, and then the Mach number depends on the speed of sound, which depends on the state of the fluid. So here you have air at 220 Kelvin and then air at 300 Kelvin, and you have the changes in those. So if you have velocity staying the same, right, the plane's still going 320 meters per second, right, in both situations, but just the air temperature is different, then your Mach number is going to change as well. Because remember, the temperature drastically affects pretty much everything that we talk about. Temperature just has a profound effect on densities, energy transfer, just work generation, anything, name it. And temperature has a profound effect on it. And so here you have the differences at 200 Kelvin, 300 Kelvin, and then 1,000 Kelvin, and those changes between air and helium. And while it's really important, right, the speed of sound changes with temperatures and varies with fluid, and you could see these change between air and helium, I think it's really interesting to see how they change within themselves with the change of temperature. So viscosity, a property that represents the internal resistance of a fluid to a motion, and that's the fluidity, right? And then a drag force, the force a flowing fluid exerts on a body in the flow direction. The magnitude of this force depends in part on the viscosity, because the viscosity, remember, represents the internal resistance to the fluid, to motion, right? To the fluid motion. So if the viscosity is the property that represents the internal resistance to the flow, well, then that's going to drastically influence the drag force, which is the force of the flowing fluid exerts on the body. Okay? And so the viscosity of a fluid is a measure of its resistance to deformation. Viscosity is due to the internal frictional force that develops between the layers of fluids as they are forced to move relative to each other. Okay? And then a fluid moving relative to a body exerts a drag force on the body, partly because of the friction caused by the viscosity. So this is just showing you that you can have two different working fluids, air or water, and you can have some sort of velocity, and then you'll have a drag force on either or, but they will be different. The behavior of a fluid in laminar flow between two parallel plates when the upper plate moves at a constant velocity. So here, remember, we're looking at everything normal too. So here's this XY, and then we have this two plates, 1 and 2, and this plate over here, it has a force and this has a velocity. And then you can see the velocity profile now, because only the top plate is moving, that we have this change here, right? And we can measure this change as well, the deformation of beta, or the change of beta. And then, see, we can have the change in A. And so this was where we started, and this is where we ended, right? Newtonian fluids, fluids for which the ratio of deformation is proportional to the shear stress. And so this just gives you information for shear stress and then shear force as well. So here we have oil and then a Bingham plastic. And so the ratio of deformation velocity gradient of a Newtonian fluid is proportional to the shear stress, and constant of proportionality is viscosity. So this is just showing you oil, water, and air in a rate of deformation over shear stress. So if air experience just a little bit of shear stress, it is going to deform greatly. We are going to have an extreme amount of deformation with just a little bit of shear stress. That makes sense because you can blow into the wind. You know, if you were able to put a bunch of smoke in front of you and you blew into it, right? Not really putting a whole lot of force into it, right? But you are going to experience a great amount of deformation in that smoke, okay? But you have to apply much more force to deform the water, right? And you're still not even going to get as much. And then here you have to apply an extreme amount comparatively, right, to oil to get it to deform just a little bit, right, compared to air and water. And so here's the same thing, the variation of shear stress with the rate of deformation for Newtonian and non-Newtonian fluids. The slope of the curve at the point is the apparent viscosity of the fluid at that point. So this is just showing you different behaviors, really, when you're getting with shear stress and deformation. And then here before, we talked about fluids for which Newtonian fluids are fluids for which the rate of deformation is proportional to the shear stress. And so you can see that. You can see here how you have a very even proportionality, right? It's linear, right? If you have with increased shear stress, you are going to have increased deformation. And that is somewhat, I mean, it's here, you can see here, but you see it here, but it's not so even, right? The rate of shear stress that you have to get for it to just start to deform here is way greater than if you were right here, you know, to right here. You don't have to apply so much right here to get a little bit of deformation as you do right here. You have to apply an extreme amount here. And so that's just showing you that it's not really proportional. Okay? And then we have chematic viscosity. And so for liquids, both the dynamic and chematic viscosities are practically independent of pressure, right? And any small variation with pressure is usually disregarded except for at high pressures. So what this is saying is chematic viscosity, we're not even going to worry about pressures unless it's an extreme amount because it's negligible and it's not really affecting. And that's in regard to liquids. For gases, this is also the case for dynamic viscosity at a low or moderate pressure, but not for chematic viscosities because the density of a gas is proportional to its pressure, right? Because if you start giving a gas an amount of pressure, it's going to deform or displace pretty easily because it's a gas. It's already unstable. It's already spreading out. But it behaves very differently from a liquid. Here you can see that behavior for viscosity over temperature between gases and liquids. The viscosity of liquids decrease and the viscosity of gases increase with temperature. The viscosity of a fluid is directly related to the pumping power needed to transport a fluid in a pipe or to move a body through a fluid. That's because fluids behave much more rationally when we're comparing them to gases. Viscosity is called by the cohesive forces between the molecules, which we need to hold those together in liquids and by the molecular collisions in gases, and it varies greatly with temperature. Okay? And remember, those cohesive forces between the molecules, we have more of those or stronger amounts of those in liquids versus gases, and that's why we're able to keep it all together. In a liquid, the molecules possess more energy at higher temperatures, and they can oppose a large cohesive intermolecular forces more strongly. As a result, the energized liquid molecules can move more freely. In a gas, the intermolecular forces are negligible, right? Not a lot holding them together. And the gas molecules at high temperatures move randomly at higher velocities. It speeds up. This results in more molecular collisions per unit volume per time, and therefore in greater resistance to flow. And so here you have variations of dynamic or absolute viscosity of common fluids at temperatures, and this is at 1 atmospheric pressure. And so this is just showing you hydrogen, carbon dioxide, helium, and this is just showing you the absolute viscosity and its behavior relative to temperature. And then here's a dynamic viscosity of some fluids at 1 atmospheric pressure and 20 degrees Celsius. So this one, see, you had a variety of temperatures down here, and this is just keeping it at 20 degrees Celsius. So here, this equation can be used to calculate the viscosity of a fluid by measuring the torque at a specified angular velocity. And so here you have a stationary cylinder on the outside, and then you have a shaft going on the inside, and then you have that working fluid, right, going around the shaft. So this is all of our working fluid. And you see you have these drag forces here. Okay. And you have RPM, so that's rotations per minute. And that, remember, anytime you see a dot over something, this means a rate. This equation can be used to calculate the viscosity of a fluid by measuring torque at a specified angular velocity. Therefore, 2 concentric cylinders can be used as a viscometer, a device to measure viscosity. So surface tension and capillary effects, we talked about this a little bit. So liquid droplets behave like small balloons filled with the liquid on a solid surface. And the surface of a liquid acts as a stretched elastic membrane under tension, kind of like a little, very, very tiny balloon. The pulling force that causes this tension acts parallel to the surface and is due to the attractive forces between the molecules of the liquid. Because remember, if we take the 3 different states of water, if we have the solid state, the liquid state, and then the vapor or the gas state, the solid state, those attractive forces are very strong. They are not moving. They are in line and they are stationary. And that's what's keeping that liquid together. And then when we go from that to a fully liquid state, well, we still have a substance, but it's just not as put together as the solid state, right? But it is still something that wants to stay together. And then when we lose a lot of that attractive forces by way of heat, most of the time, then we get into gases. The magnitude of this force per unit length is called the surface tension. And that's what you see at the top, or the coefficient of the surface tension, and is usually expressed in the unit newtons over meter. This effect is also called surface energy, right? Because it's keeping it together. It's those attractive forces, that those forces have energy. So we also now have a surface energy per unit area and expressed in the equivalent. Okay, so here we have the consequences of the surface tension, drops of water beating up on a leaf. So you can see these are like little tiny balloons, right? And remember, it's parallel to the surface. You can really see these. This is obviously a aerial view, but you can see that they are parallel. They're spreading out, right? Because it's parallel to the surface. A water strider sitting on top of the surface of the water, and then see an image of a water strider revealing how the water surface dips down where its feet contact the water. And so here you can see the other side where it's just kind of dipping down a little bit. So here's a molecule on the surface and then a molecule inside the surface. So attractive forces acting on a liquid molecule at the surface and deep inside the liquid. And here again, you can see this acting parallel to the surface. Okay. And then it does have those formulas down here where we define what work is, and work is the force times distance. So surface tension is the work done per unit increase in the surface area of the liquid. And then we have some surface tension of some fluids in air at 1 atmospheric pressure and 20 degrees Celsius, unless otherwise stated. So that's just a common one that we use. And then this is a free body diagram of half of a droplet or air bubble and half of a soap bottle. So you can see this thicker layer here, but that is still hollow, and how you have a force going in, and then what is coming around that air is forming that surface tension, and therefore you have the force coming back. So we have a capillary effect. That's the rise or fall in a liquid in a small diameter tube inserted into the liquid. And then capillaries such as narrow tubes or confined flow channels. The capillary effect is partially responsible for the rise of water to the top of the tall trees. And then the meniscus, the curved free surface of a liquid in a capillary tube. And the strength of the capillary effect is quantified by the contact or wetting angle defined tangent. So you can see the angle here. Whoops. You can see how it's just picking up on the side, and that forms that angle, and we have that surface tension here. And then just the opposite of a non-wetting fluid. It's like this, and we have that surface tension. But the angle is always taken like from the top, is how I like to describe it. It's right here. This is a better example of the meniscus of a colored water, so you can see here. Okay, and so here you see the difference in the wetting versus non-wetting. Okay, this, and then you have the meniscus of each. Okay, so the capillary rise of water and the capillary fall of mercury in a small diameter glass tube. And what this is really saying is it's showing you the forces that are acting on a fluid column that has risen in a tube due to the capillary effect. So it's just showing you the angles and the change in the surface tension, because this is drastically different than this, right? And we do have that formula there because we will need to calculate those. And so the capillary rise is inversely proportional to the radius of the tube and the density of the liquid. And it is dependent on, obviously, whatever you're working with. So here's the summary. Again, this is more for just talking about, vapor pressure, density, specific gravity, ideal gases, and those negligible characteristics that come from having real world situations versus ideal. Surface tension, capillary effects, what those look like, and why we would need to calculate those, because they're not completely parallel. They behave different. They definitely behave differently versus a wet versus a non-wetting fluid. Viscosity, speed of sound, Mach number, coefficient of expansion, and then of course the opposite for compressibility.